Hey everyone, my name is Jess Boyland and I'm a senior studying astrophysics at Whitman College in Walla Walla, Washington. This summer, I was fortunate enough to do research through the Simons Observatory National Society of Black Physicists Scholars Program under the mentorship of Matt and Oliver. And the topic of our research this summer was the effective halo model, analytic model versus simulations that have been run in the past. So a brief outline for this presentation. First, I'll discuss the motivations for our research, then I'll move on to some challenges, and then I'll discuss the effective halo model just generally, and then I'll move on to what I've done for my research this summer, and then I'll end on next steps for our research. So motivations. Why are we doing this research in general? So let's talk about a funny little particle called neutrinos. They were originally thought to be massless, but through oscillation experiments, they were found to actually have mass. And there are different approaches to making neutrino mass. As of right now, there are around like 3 flavors for neutrinos, and the 3 known flavors, let's say. And the sum of these different flavors is currently unknown. And generally, there is just more to be known about neutrinos. And by observing how they affect the power spectrum of the universe, we're gaining a better understanding of neutrinos that will help us in the long run in pinning them down and finding out what the heck they are. And so some challenges that we ran into with this research is that the neutrino is a very, very tiny particle, and thus it follows that its effect on the power spectrum is also minimal. And as you can see from this graph on the right, mostly looking at the black dots, which represent the Kyoto simulations. And around a K of 1, you can see a sliver of a red line just above the black plot, which represents the effective halo model. As you can see, the separation is very small, and for the most part, the graphs are overlapping. And so for our research, we had to get creative with how we plotted these graphs and kind of zoom in more just to create meaningful plots, because this plot right here isn't very helpful. It's informative, but not very helpful for like determining the effect of neutrinos on the spectra. And I'll talk about that more when I on the slides about my research. And just another challenge that we faced was that we are observing the mass fluctuations of the universe on small scales, which is just a challenge within itself. And so the effective halo model. It's a model that includes perturbation theory on top of what the regular halo model does. And what both halo models do is basically observe that all matter exists in dark matter halos in the universe. And the effective halo model, we worked with a paper that has been done by Oliver and the research group that he's a part of at Princeton. And just to talk a little bit more about what differs the effective halo model from the regular halo model is that the effective halo model has 2 free fitting parameters, which are the sound speed and the smoothing parameter. And the smoothing parameter, namely, it's used on nonlinear overdensity, whereas the previous models are on linear overdensity. And so basically a key difference between the effective halo model and older models is that the effective halo model includes nonlinearity, whereas the previous models only deal with linear parts of the power spectra, which leads to them being inaccurate. Another difference between the different models is that the older models had a hard time transitioning from the 1 halo term to the 2 halo term. And for clarification, the 1 halo term deals with mass that exists within the same dark matter halo, whereas the 2 halo term deals with mass that exists in distinct halo pairs. And the effective halo model kind of deals with that with the perturbation theory, which includes the nonlinearity. And so that's just the big difference between the old and the new effective halo model. And so something that the effective halo model doesn't necessarily account for are massive neutrinos, galaxies and weak lensing. And so for my research this summer, we focused on massive neutrinos. And here we are. Nice segue. So the effective halo model, we stacked it up with the Quixote simulations and saw like how they both compare to each other. And first I'll discuss these graphs, and then I'll kind of go into the code that I used to create these graphs. And so on these plots, you can see a red graph, an orange graph, and a blue graph. And so the red graph represents the effective halo model. The blue graph represents the older models, which had no linearity to them, or no non-linearity to them. And then the orange graph represents the nonlinear halo fit model, which is basically a semi-analytic model that is calibrated through simulations to present the nonlinear power spectrum. And so those are the three graphs that are shown. And basically what we did for these plots is we computed the power spectra and then subtracted the power spectra generated from the simulations, the Quixote simulations. And the graphs are showing the percentage difference between the graphs and the simulations. And so you can see that the effective halo model stays relatively close to the 0 line, which is very good. But you can see that the linear power spectrum and the nonlinear halo fit model don't do as well comparatively. And so, yeah, now to move on to some of the coding that I did to make these graphs. I basically ran a program that used the Quixote cosmology and generated and returned the different power spectrums for the different models. And from there, it's important to note that I used the same method for returning the optimized free fitting parameters of sound speed and the smoothing parameter as the effective halo model did. And I plotted them on the graph. And I had the mass of the neutrino as the input parameter. And so I ran this program for 4 different neutrino masses: the 0 electron volts, 0.1, 0.2, and 0.4 electron volts neutrinos. And these are the graphs that came out of that program. And you can see that once we add the higher mass the neutrino is, the more of a difference there are between the graphs, or between the effective halo model and the Quixote simulations, which is important to see. And so next steps. So we are going to focus on 0.1 electron volt neutrinos. And from there, we're going to change the code to have the sound speed and smoothing scales as input parameters instead of having them be the fitting parameters within the function. And from there, we're going to generate the power spectrum and find the derivatives of the power spectra. And from there, we'll use the derivatives to construct a Pfister matrix to observe the effect of changing the smoothing scale parameter on the power spectrum. And this will help us answer the question, like, do we lose constraining power on neutrino mass when we change the smoothing scale parameter, which I'm looking forward to. And just to revisit why we're doing this research in the first place, it helps us gain a better holistic understanding of neutrinos. And by better understanding neutrinos, we'll better understand the universe, which is, I think, why we're all in this field, because neutrinos have been around since just after the Big Bang. And so if we piece both together, hopefully you can just have more insight in the beautiful universe that we live in. And yeah. Now, before I end this presentation, I'd like to go into some acknowledgements. First, I'd like to thank Matt and Oliver for the help and support that they provided me through this whole research experience. I'd like to thank Casey, the Simons Foundation, the National Society of Black Physicists, and everyone else who was involved in making this program. It was very enriching for me, and I gained so much out of it, and I really appreciate all the work that was put into creating it. Um, I'd also like to thank the speakers who presented, who gave presentations on their research and other things, for reinvigorating my love for physics and just the STEM field in general, and having more confidence in myself in pursuing my degree. And lastly, I'd like to thank all the scholars for being so fun to get to know. It's been really lovely to just see other physicists that look like me on a weekly basis. And I hope everyone has a great rest of their summer, and thank you for this experience.